Finally, it's time to start solving linear systems. To do this, we need to define the special type of matrix. So a matrix is said to be in row echelon form if 1. Any row of all zeros is at the bottom of the matrix. 2. If I choose a non-zero row and start walking along it from the left, the first non-zero entry I hit is a 1. This is called a leading 1. And 3, the leading ones make a series of steps going down and to the right. We'll see what I mean by this in a second. So that takes care of row echelon form, but there's also a reduced row echelon form, or RREF. And to be in RREF, the matrix must be in row echelon form, but also each leading one must be alone in its column. All right, let's write down an example matrix and see if it's in RREF. So to determine whether this is in RREF, let's go through the steps. There's a row of all zeros and it appears at the bottom. So yep, property 1 seems to hold. Property 2, for each of the other rows, if we start from the left of the matrix, let's highlight the first non-zero element we encounter. These are all 1s, and thus our leading ones. And so yeah, property 2 holds. For property 3, each leading one must occur to the right of any of the ones above it. In fact, notice this staircase-like pattern made by the leading ones. That's what we needed for property 3. All 3 properties mean that this matrix is in REF. If you look up the word echelon, you'll see that it means step, level, or grade, just like the blue staircase you see above, hence the name. All right, is this in reduced row echelon form? Well, the answer is no. Look at these 2 leading ones. They need to be the only non-zero element in their columns, and that's just not the case. All right, so here is a similar matrix that is in RREF. Take a moment to verify that all 4 of the properties are satisfied. And so a question is, why RREF? Why do we care? Well, if our matrix represents a linear system, each of those zeros corresponds to a variable which just simply doesn't appear in the system, right? It's been eliminated. So putting a matrix into RREF simplifies the linear system. So looking ahead, what we're going to do is we're going to use the elementary row operations to transform matrices into RREF. And it's worth pointing out now that the reduced row echelon form of a matrix is unique. However, there are actually infinitely many row echelon forms, so that'll come up. All right, Gaussian elimination. This is the algorithm that we use to convert a matrix into either REF or RREF using elementary row operations. And now this process isn't complicated, but it does take some practice to master. So let's go back to the toy example we've been carrying around. Roughly, the algorithm is as follows. So anytime you get a row of zeros, use the interchange rows operation to stick it at the bottom. In this case, we don't have any zeros, so we're just going to go to the next step. So now I'm going to choose a non-zero row to contain our next leading one. In this case, I'm just going to choose the first row, which means that this 3 here is going to become a leading one. And to get this step-like pattern, we're going to use the EROs to turn everything beneath the 3 into a 0. And that requires a little bit of thinking to do. So there are many ways to do this, and the way I'm going to do it is I'm going to multiply the first row by 2 and the second row by -3 and add them. And if you do this, you'll see that the x coefficients cancel, and so putting that into row 2 gives this matrix. If we had more rows, we'd now choose a new one and repeat the process until we ran out of rows, but we're out of rows. So our matrix should now have the rough outline of a staircase, and so we need only make each element into a leading one. That means scaling row 1 by 1/3 and row 2 by 1/10. And voila, there's REF. Now remember that elementary row operations don't change the solutions, so the system corresponding to this augmented matrix has the same solutions as our original linear system. We can immediately read off half of the solution in y is equal to 1/2, and if we can then find the x term by substituting this into the first equation. Solving for x gives x equals 1. This process is called backward substitution, and it gives us our usual solution that we know. All right, so what about reduced row echelon form? Well, to convert to RREF, we now start at the bottom, and we're going to use the elementary row operations to eliminate all of the non-zero elements in the columns containing the leading ones. So let's rewrite our REF matrix here. To eliminate the 2/3 term above the bottom leading one, we'll take 2/3 row 2 and we'll add it into row 1. So we're now in reduced row echelon form, and let's take a look at this system. We can just immediately read off the solutions. So the advantage of RREF is that it represents the simplest linear system that has the same solutions as our original linear system. Okay, time for some important notes. There are many paths to RREF. Okay, practice will teach you the tricks to choosing the best possible EROs and making your life as easy as possible. And second, Gaussian elimination involves a lot of arithmetic, and so it's really easy to make mistakes. So you want to practice a lot to get good at it. All right, it's time to do a bigger, more complicated example. Let's solve the following linear system, 3 equations, 3 unknowns. And before doing anything, we're going to write down the augmented matrix that represents this linear system. Okay, so the 1, 1 element of this matrix is already conveniently a 1, so let's use it as our leading one. Multiplying this row by -2 and adding it to the row beneath will eliminate the 2 directly beneath it, and similarly -4 into row 1 will eliminate the 4, and what we're left with is this ugly matrix. Now we move to the new row. I'm just going to make my way down the matrix, so I'm going to take -5 as my next candidate. And to get rid of that -12, we're going to have to think a bit, but multiplying the second row by 12 will give us -60, multiplying the third row by -5 will give us +60, and if I add those two things together, it'll result in a 0 in that 3, 2 position. So look what happened to row 3. 26 is this nice multiple of row 13, so let's use this opportunity to rescale row 3. And if we wanted to turn this into REF, we'd need to now only rescale row 2 by -1/5. And you could then use backward substitution to find x, y, and z. And in fact, you should stop the video now and do that. All right, so instead of doing backward substitution, though, I'm going to go straight to RREF. And if we start at the bottom with this 1 here and eliminate all the non-zero element above it, so -4 and +2 should work quite nicely to eliminate these terms. So we'll work that out and we'll get this matrix. Row 2 is now finally in a nice position to be rescaled, so let's do that. And now that we have a leading 1 in row 2, we'll eliminate the 3 above it. This matrix is now in reduced row echelon form, and as a system allows us to read off the solutions. So 1, 1, 2 is our answer, and that's how we solve linear systems.